In this series of videos, we'll talk about linear regression and least squares. And the problem that we'll be solving is, first in the most abstract setting, if you're given a subspace W of Rm and a vector, let's call it B, also in Rm, the question that we want to solve is, which vector W in this subspace W is closest to the vector B? Now, just intuitively, if we take the orthogonal projection of B onto W, let's call that P subscript capital W B, so the projection of B onto the subspace W, the orthogonal projection, we suspect that that would minimize this distance. And the distance, so the distance that we're trying to minimize is B minus W. Minimize this over all W inside of this subspace W. Equivalently, you can minimize the square of the distances. And this is why this problem is called least squares, because we're minimizing the squares of each of the components of these differences when you add them all up. So that's the statement of the problem, is to find W inside of W such that the distance between W is minimized. And it turns out that the solution to this problem is exactly W equals the projection of B onto W. And I won't give a precise proof of this statement, but we should at least get an intuition for why this is true. Looking at this picture, I've already drawn the projection of B onto W and another arbitrary vector W. Now, these three vectors form a right triangle. So it looks a little bit skewed from this angle, but if you turn this way, that triangle looks something like, here's B, here's the projection of B onto W, and here's some arbitrary vector W in the subspace W. These two vectors are in W, and so this line connecting them is also in W. The vector B is perpendicular to the subspace W, and therefore this angle is a right angle. Here, this is the hypotenuse of this triangle, and it's the distance from B to W. And this distance is the minimizing distance, supposedly. So that's just B minus the projection of B onto W. So I misused a little bit of notation here. I hope you understand that this W now is different from this one. This is the actual solution. And because this is a hypotenuse of this triangle, we know that this distance is always going to be greater than or equal to either of these two distances. No matter what W is, this will always create a triangle, a right triangle, unless W equals this vector right here. And in all other cases except this one, this distance is always going to be strictly greater than this distance. So what are some ways to compute this projection? So one way is to actually find an orthonormal basis of W. So given an orthonormal basis, let's call it W1 up to WK. Let's say K is the dimension of W. Then the projection of B onto W is just take the dot product. Remember, the dot product of B with any of these orthonormal vectors gives you the shadow of B onto that vector, and then multiply again by that vector here to give you the shadow of B onto this line in that same direction. So we take the dot product or the inner product. I'll write the inner product with brackets of each of these vectors. And then we'll multiply by that vector again so that we have a vector in the end, and then sum up all of these different contributions from these different shadows. So this is how you would compute the orthogonal projection of a vector onto a specific subspace. You would need, for instance, an orthonormal basis for that subspace. But sometimes you're not given an orthonormal basis, so it might be difficult to compute it. One thing you could do is you can choose any basis of W, pick arbitrary vectors that are in W, and once you find k of them and you know that they're linearly independent, then you know that that forms a basis. Then, in order to find an orthonormal basis, you would apply the Gram-Schmidt procedure to obtain an orthonormal one. But you know how difficult that is. Maybe you can do it for the first few vectors pretty easily, but then after a while it gets pretty messy. So we'll look at a special case of this problem where W happens to equal the column space of some m by n matrix, where A is an m by n matrix, m by n matrix. So in other words, you can think of A as a linear transformation from Rn to Rm. And in this special case, we'll find a very interesting solution to this problem. In general, when we look at this problem and we're given a vector B, so now let's suppose that this subspace is the column space of A, and we have some vector B that's not necessarily in the column space. What this means is that the linear system AX equals B does not have a solution unless A is onto, or more specifically, or more precisely, unless the vector B is in the column space of A. But because this doesn't happen in general, instead of trying to solve this system, which might not have a solution, we can solve an associated system instead that says, OK, I might not be able to find an x in our domain here that sort of maps to the vector B, because it's impossible all x's get mapped to this subspace. What instead we can try to find is project B onto this subspace. And now this vector, the projection of B onto that subspace, is by definition inside the column space of A. And therefore, we can solve that associated system. So we make a definition based on this idea that a least squares approximation to the linear system AX equals B is a solution to the associated linear system AX equals the projection onto the column space of A applied to our given vector B. And it's this problem that we'll be focusing on solving in the next few videos.